Open the spectrophotometer program called Scan. While the program is booting up, make sure your cuvettes are filled to the line with a solution, but not over this line.
Now we have to zero the spectrophotometer using a blank, which in this experiment is filled with deionized water. Wipe two sides of the cuvette and place the cuvette inside the spectrophotometer. Click 0 and the absorption reading should be approximately 0.
After zeroing the spectrophotometer, take the blank out and place the stock solution used in this experiment into the machine. Allow the machine to run. The machine should give us a graph of absorption of light for the sample across all of the visible light spectrum. Look for the wavelength with the highest absorption, also known as lambda max for the solution. It will be the part of the graph that has the highest peak. This wavelength will be the best for determining the relationship between absorbance and concentration, since this wavelength has the best absorption for the solution. After you determine the lambda max, open the Simple Reads program and click the Setup button and input the wavelength into the machine. Zero the machine with the blank again, and then put this first serial dilution into the machine. Make sure to clean two sides of the cuvette that the light will pass through. Click the Read button and allow the machine to run. Place the second serial dilution into the machine after wiping two sides of the cuvette. Don't forget to record your data and keep track of which solutions you have measured. The machine will label each solution as you go. It is best to start with your first serial dilution and go through the concentrations in descending order and ending with the unknown so you can best see the relationship as the experiment is running. Make sure to use actual chem wipes and not paper towels to wipe your cuvettes. After you have measured the absorbances for all your dilutions, record your data in your lab notebook. Don't forget to clean your workspace when you are done.
Now that we have gathered all our data, we can use Beer-Lambert's law to determine the relationship between concentration and absorbance and find our unknown.
Beer's law states that absorbance depends on the wavelength-dependent molar absorptivity coefficient for the dissolved substance at a specific wavelength, which is lambda max in this case, the length the light travels, which is the cuvette's width, and the molar concentration for the substance. This gives us an equation, A is equal to epsilon times V times C. It is important for this reason to zero the machine using a blank so that the solution used to dilute the substance we want to find is not factored into the absorbance. In short, absorbance is proportional to the concentration. Using the calibration curve of a substance concentration versus absorbance, we can find a linear relationship. To find M, we take two different points of absorbances and subtract them. In this example, we took 1.1974 and subtracted it from a different absorbance, 0.2236. On the denominator side, we subtract the initial value's concentration, 0.02, from the final concentration, 0.0032.
Now that we have the slope, m, we can plug the value back into the equation and get y equals 57.96x.
We can then plug the unknown concentration's absorbance back into this to get 0.3123 is equal to 57.96 times x. We can now isolate x, which is the concentration of the unknown, by dividing 57.96 and get the concentration to be 0.005388 molarity.